Welcome to Chapter 6. In this video, we're going to do something new and exciting. We'll be looking at the first derivatives of our base p trig functions. Let's just get right into it. We'll start with the derivative of sine base p. Here I'm taking the partial derivative because all of our base p trig functions are technically multivariate. It is possible to differentiate with respect to p, but for now we'll only be doing it with respect to x. Now back to the task at hand. Since sine base p is height base p times sine, we'll have to perform a product rule in order to find the derivative, which then means we have to find the derivative of height. Now this is a derivation that's full of chain rules and simplifications. If I were to show every step, this video would become very difficult for all of us to get through. However, I do encourage you to derive this and future lengthy derivations yourself. What I'll do in these videos is hit on different points after doing a few simplifications or before explaining the next step. Back to the derivative of height, we'll first use the power rule since we're treating p as a constant, and multiply by the derivative of the inside because of the chain rule. For the next step, I want you to recall the derivative of the absolute value that we defined in Chapter 5, this time with the chain rule shown. Looking at the absolute value of cosine, for example, its derivative will be signum cosine times the derivative of cosine, which is equal to negative sine. You should also note how I rewrote the exponent on the left from a negative 1 over p minus 1 to a negative 1 plus p all over p. This form should be familiar as the definition of height base p, but raised to the p plus 1 power. We can distribute p height base p's into the parentheses, and we end up with this expression, which I will not be reciting. Now this form is pretty hefty, all things considered, but it can be reduced into this. However, the expression on the bottom is not continuous at any integral multiple of pi over 2, which means it doesn't represent the derivative at those points. Second, however, the bottom expression is actually equal to the derivative at p equals 1, but for no other values of p. When it comes to this area of Squircle math, there are a lot of caveats that come about because of the signum function that would be frustrating to always go through. What that means for these videos is that I will always try to call the final form one that has the least discontinuities, which here is the top expression. That doesn't mean that the bottom expression isn't useful though. Finally, going back to our sine base p product rule, we can plug in our reduced height base p derivative. Now we can factor out a height term, then distribute the sine. Using the sine cosine Pythagorean identity, we can simplify the second half of the parentheses. Getting clever, we can turn the cosine into a cosine squared over cosine, and use the Pythagorean identities again to get this tiny little thing. And since this form has discontinuities at integer multiples of pi over 2, we have to do a little rearranging. We'll multiply the numerator and denominator by height base p of x, then multiply in 2 signum of cosine base p's, creating an absolute value in the denominator. As a note, signum of cosine base p is equal to signum of height base p times cosine. Since the signum of a product is always the same as the product of signums, and height is always positive, signum of cosine base p is the same as signum of just cosine. Anyway, we can move the absolute value of cosine base p up, and our result is that the partial derivative of sine base p with respect to x is signum cosine x times the absolute value of cos base p of x to the p minus 1 times height base p squared of x. Using this, we can derive the derivatives of the other three functions without having to go through that tedious simplification. We can plug a pi over 2 minus x into sine base p and rewrite the derivative like so, with a negative 1 tagged on because of the chain rule. Once simplified using reflectivity, we get cosine base p's derivative, which replaces the cosines with negative signs. Using cosine, we can find the derivative of secant base p by referring to secant base p as cosine base p to the negative 1. After simplification, we get a similar form, this time with the negative height squared becoming a secant squared. Doing the same process, or using reflectivity for cosecant, we get the same as secant, but it's negative, and each trig function is now its complement. And there we have it, our base p trig first derivatives. I think it's cool to see that all of these are in similar forms, which are related to each other. For the functions that are reciprocals of each other, they have the same signums and absolute value of base p to the p minus 1s, which is its complement, respectively. For the functions that share their reciprocity, they have the same idea of that final squared term. Sine and cosine have hype squared, and cosecant and secant have cosecant squared and secant squared, respectively. And for the functions that share a prefix or have the same complementary status, so to speak, they share the same sign put in front. The non-complementary functions have a positive sign, and the complementary functions have a negative sign. As a final note, I encourage you to check out on your own how these derivatives match up with the more well-known circular trig derivatives when p equals 2. As we move forward and as you look back at previous videos, checking that they hold up when p equals 2 is both satisfying and a good way to feel like we're on the right track. See ya!